Right, we're gonna do our final part of our stoichiometry notes, mainly talking about percent yield. This is limiting reactants, and these problems get pretty long and hard, so we're just gonna talk about a little bit of vocabulary, not really any problem. If you miss school on this day, we need to go into the previous classroom picture. So limiting reactant is a more realistic, I believe a more realistic setting or more realistic idea for reactions. We've been doing them as I want people to paper like they work out perfectly. Then in real life, usually you have your reactions and one gets used up and causes a reaction to stop, and then you have one reactant that has a lot in excess or some left over. And so these specific types are called limiting reactant problems. And like I said, we're not really going to do the problems just a little bit. So you can recognize these by the fact that you have two reactants, and they both have a starting not given in the problem. And so if we were to do these problems, we would have to do two stoichiometry problems. When you do those two stoichiometry problems, whichever reactant produces the smallest amount of product, that's called the limiting reactant. And the limiting reactant is a reactant that is used up first. So because of that, it's the one that controls how much product is made. Once it's used up, then the reaction stops. So then that leaves your other reactants being the excess reactant, or meaning that there's some of that left over. It's not completely used up. And so if in real life and there was some type of problem going on, like in sorry, my mind, a factory or something like Phillips or something where there are Celanese where they're actually making something, one of the reactants may be real expensive, so that may end up being the limiting reactant, and they may just flood it with the other one, because if there's some excess of that left over, it doesn't really matter. But what we're really going to spend most of our time on today are percent yield problems. And percent yield problems look at the efficiency of a reaction. When we write our reactions, we act like everything works out perfectly, and I calculate this much of the product is made, but in reality, it doesn't usually work like that. Some of the product is usually lost. Could be something as simple as human error. Some of the other reasons you have listed here, many reactions do not use up the limiting reactant completely, and this could be because molecules aren't arranged correctly. They don't hit each other with enough energy, but for whatever, not all of the reactant is used up, so you don't get as much product as you calculated you would, or as you thought you would theoretically. Reactions are oftentimes reversible, so that means if I build up a lot of product, then I end up having a lot of product built up, and then that causes a reaction to reverse, and it goes back to the reactant. Most reactions would have to be purified to collect the product. It could be as easy as trying to drive off some water, and that sometimes causes some of the product to be lost, or sometimes there's some side reactions that are happening, and that has used up some of the reactant. Like I mentioned earlier, simple as human error. Reactants or products are leaked or spilled. They may not be 100% pure. They may have got some impurities in them. And then sometimes the reactions occur so slowly that they stop before all the products are formed. So to do your percent yield, you need two numbers. You need the theoretical yield, which is the expected amount of the product from a reaction. So this is the answer to the stoichiometry problem. This is your calculated answer. This is how much
of the product you would get if everything was perfect and none of those little reasons we talked about previously happened. Actual yield is the actual amount of product that comes from the reaction, and it can only be determined in the lab. It is what is actually made when that reaction occurs, and you're looking for words like produced or formed, isolated, to give you a hint that that's the actual amount. The actual amount always has to be given in the problem. The theoretical could be given in the problem. That makes it a lot easy, or sometimes you have to calculate the theoretical. The higher the percent yield, the better the results, and companies make more money. So they would love a 100% yield, but that doesn't actually occur that often. So here's our actual formula that we're going to be working with. Percent yield is equal to actual yield, which is always given, and theoretical yield, which may have to calculate. Actual yield is less than or equal to theoretical yield, and it's usually less than, because we're usually able to actually make less than what we theoretically thought we could. So that means when you're doing problems, if you get a percent yield that's over 100, then you probably have flipped your number. So you need to go back and look at that. So these examples that are in our notes are a little bit harder. So we're mainly going to look at some on practice, but I am going to show you this one right here. This is a real easy one, because on this particular one, you're given both the actual and the theoretical. So remember, my formula is percent yield is equal to actual yield divided by theoretical yield times 100. So it says if 12.5 grams of copper chloride was actually produced, so that straight away tells me that's my actual amount. But 12.5 grams of copper chloride was calculated as a theoretical. So they're giving me the theoretical. I'm not having to calculate it. What is the percent yield? So on this particular one, we would just plug in our numbers. Our actual, which is my 12.5 grams, divided by my theoretical, which is my 2.54 grams, and multiply by 100. And we'll, excuse me, we'll round that to like 2 places past the decimal or 1 place past the decimal. So top number minus my bottom number would be 49.2%. So remember, when you're looking at percent yield, you're always finding the percent yield of a product. It doesn't make any sense to find the percent yield of a reactant. Also, remember your number, smaller number, actual should be on the top, your larger number, theoretical should be on the bottom. And sometimes you have to calculate the theoretical. So let's look at the worksheet for a couple of more examples. All right, so we got daily work. For Wednesday, I can't remember. Yep, Wednesday the 10th. So you have a mixture of different kinds of problems in here. You have some that are going to be real simple because you're going to be given the actual and the theoretical. And then you have some where you're going to have to calculate the theoretical by just doing a simple mole to mole problem. So we'll look at our first one. It says this reaction produced 20 grams of potassium hydroxide in the lab. So that is my actual. And remember, we're always dealing with a product. That says that's how much was in the lab. And we're going to be using our formula for all these. I'm just going to shorthand it as actual divided by theoretical times 100. And then it says the theoretical yield was 12.5. So once again, I'm giving it, I don't have to do stoichiometry to figure it out. So I'm going to take my 20 grams, divide by my 21.5 grams, and multiply by 100. Top number divided by my bottom number, and I would get 23.02%. So that's a real easy one. On B, that's exactly like that, another easy one. There's several in here that you are going to have to calculate the theoretical yourself. And I kind of give you a hint that that's what you're going to have to do because it doesn't say what the theoretical is. So it says, if I start with 5 moles of this hydrocarbon, what is my theoretical yield of water in moles? And I tell you that you have to calculate that to get the theoretical. It's not going to be given to you. So you're doing a mole to mole problem, the simplest kind that we did right at the beginning. You don't have to have any molar masses. So I have 5 moles of this hydrocarbon, and I'm interested in water. So all we need here is the mole ratio. For my hydrocarbon, I have just 1 mole because it doesn't have a coefficient. And for my water, I have 4. So 5 times 4 would give me 20 moles of water. And that is my theoretical yield. I had to calculate it. If everything was perfect, I should be able to get 20 moles of water. If you go to 2B, it says, using your theoretical yield from the previous problem, what is the percent yield if 10.5 moles of water was actually made? So that's my actual amount. So I'm going to do my percent yield is going to be equal to my actual divided by my theoretical that I had to calculate and multiply by 100. So 10.5 divided by 20 and multiply by 100, I get 52.5%. And that would be my theoretical. So the rest are like that. There's quite a few that are this easy. You just fill them in. But there's some that it doesn't give you the theoretical. If it doesn't come out and say the theoretical is this amount, that means you're going to have to do a mole to mole problem to get your theoretical and then use it along with the actual to figure out the percent yield. All right. And you will, of course, see some of these on the test on Tuesday. All righty. Thank you.